Welcome back, everybody. Oh, what a week, what a week, what a week. I spent the majority of my week in Ingram, Texas, trying to do recovery efforts. It's still a mess down there. We had another flood yesterday, so yay us. And that kind of resets the whole recovery effort because basically all the debris, everything we've gone through, is almost kind of resets because now while this flood wasn't anything to the scale of the first one, it still moves everything around, it still uncovers stuff, it still does a lot. And we're also starting to find that, shockingly, under the riverbed there is a massive amount of material that got buried in the bottom. Anyway, I'm technically not supposed to talk too much about it, but uh, yeah, that was the majority of my week last week. So yeah, yes, but we're doing good, and it is Monday, and we're gonna have a great day. We're gonna have a great week, and we're gonna talk some chillers today. I see we got Mr. Froggy himself in the chat. We're gonna get to that question in just a second. I hope y'all are doing really well. Um, yeah, things are moving along. I'm very excited with how the academy is coming along. We're making a lot of progress in there. I say we, I. Um, but yeah, we've got some fun initiatives and some fun stuff coming up. Getting a lot of the updates and stuff I've been trying to work on for some time done in the certification course, and then getting more material added into the service program as well. It's just really exciting stuff. Exciting to get uh, the progress going as smoothly as it has been recently. So, with that, feel free to get your comments into the questions. I know with the swing of things, not everybody is. Everybody kind of got out of the habit of using the portal inside of chilleracademy.com for the series here, Chiller Questions Answered series. So feel free, if you want to get your questions prioritized and have more direct follow-up with me, you can use that portal and you'll see all the previous recordings and stuff, but I prioritize that if you want to use that over at chilleracademy.com. And then from there we get into the comments, questions, and I still have a pretty good library of questions that have come in over time that I've saved that I still want to try to get an answer to, even though I may be quite a bit behind on actually answering them. Either way, let's get into this one. Duplex chillers separate refrigerant circuits. How that affects heat exchangers approach readings when, for example, one is offline, there is some gain if single pass, evap, and offline is downstream. Yes, okay. So let's go over here to the whiteboard real quick. Let's just kind of clarify a duplex. Now, in a duplex scenario, there's two ways that a chiller like this can be done. You have so this is, say, your evaporator, and this evaporator will have a divider plate down the middle. And essentially, it's two individual chillers. Okay, so let's say this is our compressor. Okay, yay, my drawing. So we have two compressors sitting up here. This is a centrifugal style machine. So when we say duplex, this is what we're referring to. So we've got, and each of these compressors has their own independent circuit pulling off this evaporator. Okay, and we've got our water connections over here. So whether it be so a lot of duplexes, or let me stay on track here. Okay, so we could have a two-pass or a single-pass scenario depending on what the chiller is doing. So we could have one water connection here, one water connection here, and these are, like I said, independent circuits from one another. Now, you could also look at, even though I don't see these commonly referred to as duplexes the same way, where you have two compressors, but they're the same refrigerant circuit. Okay, so this would be an example of a CDH by Train, and this would be an example of a YD by York. So this is one single circuit. They're both serving the same refrigerant, where in this example, they're actually having two separate refrigerant circuits entirely. They don't share anything at all. They're literally just two chillers sandwiched together. Really, you could almost think of this as a series circuit. So in some cases, you can actually run. So we're going to move on from here. You can actually run chillers in series with one another. So say your evaporator, you got a compressor, okay? And say a lot of times these will be a single pass. So it'll leave this chiller and then flow into the very next chiller. This is your evaporator water specifically. And this would be a series type of control. So the water flow would be coming through. So there's a few ways of doing that, but this is basically what this becomes, just in a more condensed fashion. We don't have a separation or break or piping in between these. This is just one central system combined. Now, how does that affect your approach or your readings? It is my assessment that it should be mostly minimal, depending on which circuit though it would be on. So with these are going to have a lead lag style of controls. So one is going to take priority, it's going to ramp up. Once it gets to a certain stage, it will then try to bring on the second compressor, and it will ramp up, and it's going to have a normal lead lag control circuit like we would typically expect with any screw compressor, or if we had multiple centrifugal chillers, in the same plant. They're going to have a lead lag control circuit. These would do the same. Now, depending on which circuit is in lead and what direction your flow is in, is going to affect the water temperature coming in. So when both of these are online and we have flow coming this way, then our warmer water is hitting this side, and we have it. It's going to be partially processed down, and then this side is going to have the rest of the water hitting it and having to process down further. So we may be coming from, say, 60 degrees down to, say, 50, and then 50 to 45, 42, 40 degrees, whatever it is on this side. And that can be challenging because getting an accurate entering water from this point into this side of the evaporator doesn't really work the same like we would when they were fully separated, or if they were parallel to each other instead of in series with each other. So that does have it has an impact in that way. Now, if let's say this chiller was in lead, okay, this is our lead. I guess LL didn't help us. This is our lead, this is our lag. Then you mentioned that there would be some heat gain with passing through here, which that is going to have some truth to it, but really it's not going to be that much if we're passing through this side of the heat exchanger and leaving on this side. Now, to your point though, if this was our lead compressor and we were leading over here, then this whole kind of non-processed zone of the evaporator is likely to see some gains. But we're still going to be controlling based off of leaving water temperature to begin with. So what the chiller would do is it would compensate a little bit so that technically the water leaving this half of the evaporator might be a degree or two cooler than the actual set point, but by the time it gets through the other evaporator side of the tubes, because the tubes through here are the same, there's no break or anything in the tubes, it's just a break in the refrigerant circuit. So by the time it processes through here, then we're at our, say, 42 degree set point leaving this side of the chiller. So that would be a way that it would compensate. Now, on the approach itself, there should be fairly minimal impact, in my opinion. Now, if you had a 2-pass style with one of these, then part of what's going to make that extra challenging is we'll kill this side. Okay, so we're coming in. Now we've got to come through both sets, go through our water box on the other side, and then come back out. Say this was our lead compressor. This whole section of pipe is just friction gains. Okay, so flowing through here, we're not having any refrigeration effect happening, and we're going to be coming back out over here. I would expect something like this to increase your approach, I'm going to say marginally. And you're talking a very part load condition at this point. So these machines are designed to try to run at higher loads to begin with, but they have the ability to turn down pretty far to where they can run at a fairly minimal load when they need to. So that would be like a standby load on a process system is where I would expect to see something like this. So we know that we have high load demand. That's where we typically are at, but we also have breaks in the process cooling that we need. So we would end up instead of shutting the chiller completely off, which is not ideal, we can cycle down heavily, say we get down to the lead compressor at a minimum stage, something like that. Yeah, you're going to see some pretty good approach increases, 1-2 degrees, something like that, because the chiller is still going to try to achieve leaving water set point. And I'm realizing I have these backwards. This would be our out, this would be our in a more literal sense. Anyway, we would still be trying to achieve leaving water set point, but to do that, because we're gaining some heat over here, we would likely see this refrigerant temperature pull down just a little bit more in order to get the leaving water over here. In some cases, I don't know that that would be true in every case, but in some cases, it wouldn't surprise me to see that. So I don't think so. To stay to the core of the question, how would that affect the heat exchanger's approach itself? I don't think it would be a major effect. But this is the overall concept of a duplex, and so these would be examples of simplex. Okay, so this would be your simplex machines, just run in series, and this would be a duplex where we take two simplexes basically and merge them into one and make them a 2 compressor system. And this is in the context of they have a separate refrigerant circuit specifically, and they're not sharing the internal refrigerant circuitry like a YD would. So, yeah, that would be my high level answer to that. If you're still curious about that further, I can try to expand on that a little more if I need to. Very good question, though. I'm curious, are you seeing very many duplex machines out there? I know you recently started up with a new company, which, given what y'all are doing, it wouldn't surprise me if y'all had a lot more of that type of equipment on hand. So are you seeing that? Okay. We will move over to our next question. Let me go grab it. Okay. What types of chillers are likely to have falling film versus the standard kind. Okay, so by falling film and by standard, what we're referencing there is a flooded versus a falling film, or in some cases, hybrid falling films depending on the setup. So let's come over here to our whiteboard. So let's kind of identify a difference in what these are at the moment. So looking at it from the water box side or the in-bell side, okay, so these are to be two separate evaporators. All right, we got our tubes. Okay, this one on the left is going to be what a flooded design. Okay, and we need to define, just make sure we're all clear on the separation here. This over here would be a falling film. So this would be a falling film setup, and we would have a set of baffles here with a distribution rail, and then our refrigerant coming in would come in as high pressure up here and tap in. Okay, and then our suction gas would still come out the side up into our compressor. Okay, this would be our suction vapor. So a falling film, what is happening is right here we're hitting our metering device, and then we're flashing off into our distribution rail. So we come into the distribution rail here in the top of the evaporator, and it sprays a mist of the refrigerant over all the tubes in here, and that mist rains down over the tubes. So the refrigerant's on the shell side, water is on the tube side. And then by the time we're getting down here to the bottom of our tubes, we would expect that the vast majority of that refrigerant to have evaporated off or boiled off, and we would just have maybe minor little pockets of liquid down here at most, typically. Now this is with a true hardcore falling film, or something like I would give an RTHD as an example of this, or a YVAA. Those would be examples of a more traditional falling film where there is some liquid refrigerant that does stack on the bottom of those, and I think those actually do have some tubes that do get down and touch on that liquid refrigerant. So it's not that there's no liquid refrigerant in the bottom of our applications where we see this on the chiller side, but it's very, very little. And the YVAA, has a side glass over here where you can see through. The RTHDs have their liquid level control sensor, which this is what runs the metering valves. So this would be a falling film, and yeah, all this kind of boils off and up into the compressor suction. Now, a flooded, on the other hand, we're going to have our liquid refrigerant come in to the bottom of the barrel. So this is one way to tell them apart. So this will be our metering device. This is where we flash off, and we're going to feed into the bottom. Now there is still typically a distribution rail here at the bottom of the evaporator, and to make sure we distribute across the full length of it. So we do have some management there, but we're just injecting that saturated liquid up into the evaporator from the bottom side, and our goal here is we want to maintain a liquid level up to the top of our evaporator tubes. And so most of the time there'll be a screen mesh right above the tubes and where the liquid level will be. So we want the liquid level between the top of the tubes and that screen mesh. And that screen mesh helps make sure we don't have any liquid droplets make it up into the compressor. It also helps kind of act as like a distribution on the pull of the suction. So like right here, we've got these baffles that pull the refrigerant around the tubes and give it space to kind of flow without having this mist accidentally pull into the compressor suction. So that's where this will call it baffling plates. That's why those are there. Over here, using that eliminator, which is just a mesh screen, we can we're doing the same basic effect and function, just in a different way. So yeah, a compressor suction then comes off the top, refrigerant boils off, comes up into the compressor. So there's the core difference between these two styles of evaporators. Now, in terms of the core question, uh, which was what types of chillers are likely to have falling film versus the standard kind, it's going to come back to newer machines are going to be favoring this falling film design or hybrid falling film design, which, to very briefly get into, essentially with a hybrid falling film, we run a higher liquid level, and I guess I should draw it. So we still have the upper section of tubes like this. We still have the distribution rail and the baffling. But then down here at the bottom, we have an intentional set of tubes that are going to stay submerged. Okay, so it's quite literally these two kind of combined into one. And then we're going to try to maintain liquid level right there in the middle. And then, you know, a YK would be an example of this. YKs will use a hybrid. And this is something I was taught to refer to this as a hybrid, even though I'm talking to factory guys, they don't necessarily think of it that way. But this is a hybrid style of falling film because we are still intentionally submerging some tubes in a way that we're not necessarily, it's not as intentional here. I'm not saying tubes don't get submerged at all at the very bottom, but it's not the same thing. This, you might have a couple of inches of liquid level. This, you'll have maybe a couple of feet in some cases, depending on the scale and the size of the machine, and all that's intentional and part of the design. These will also still have the liquid line inject into the top, coming into a distribution rail, separate from these, or from the falling or a flooded design. So we're seeing these two take a lot of precedence, especially on, I would say, smaller machines. So we're talking about screw machines. I see the falling film, a more true falling film design implemented a lot more and a lot heavier. And then on some of the larger ones, say a YK would be the example I'm using here. This is where I'm seeing them implement kind of this hybrid design. Now, they still refer to this as just a falling film. They don't use the hybrid term. That's something I use to differentiate these because they are different in that way if you look at it from a very, say, purist perspective. I guess that's how I would say I'm kind of coming at this is hard definition. I wouldn't define this as a true falling film. Okay, that's my sticking point. I'm going with there. Anyway, so yeah, your screw machines, RTHD like we're talking, or a YVAA, that is where we're seeing these implemented. And then on your, say, larger, specifically centrifugal type machines, we're seeing this implemented. Now, it doesn't mean the flooded specifically gets used on both sides of that, whether it be screw or centrifugal. But your newer, more modern, and higher efficiency designs are trying to go with a falling film, either of these style, for a couple of reasons. One, in terms of efficiency, these are very close. They're close enough to a flooded's efficiency to still be practical and keep our size down. So that's one of the key benefits to chillers is we can fit a lot of cooling capacity into a smaller package. It's not as big of a machine. And so as compared to, say, what it would require if we had RTUs and split systems, like things of that scale, compared to this is where we really shine, is we can fit a whole lot of cooling into a fairly small total space comparatively. So what's great about flooded is we maximize how much heat process we can have in such a small confined space. The problem with flooded is it takes a huge amount of refrigerant to get all those tubes fully submerged. And then as these machines scale into larger sizes, that problem only gets much worse. Like, it takes a massive amount of refrigerant comparatively. So one of these, on the other hand, we're not trying to hold a huge volume of liquid refrigerant in the evaporator. We're just at most a small volume to a moderate volume. So that greatly reduces how much total charge that machine requires. But efficiency-wise, we can look at our approach value as a metric of that efficiency. These run the same approach values, and they're designed to run the same. Now, you may see that a falling film evaporator may be slightly larger, if you can even tell the difference in terms of physical size. And I would say that I would argue that comes back to, it's not the exact same level of heat transfer as a flooded, in terms of we will need more surface area, because while we're raining liquid refrigerant over the tubes, they're not literally sitting in liquid refrigerant. I think it's one reason why York really likes this hybrid design so much, is because it does kind of incorporate both the best of both worlds. Anyway, so because that's so much less refrigerant, but we still have the same efficiency, that reduces the cost of this a lot. But we keep a very similar size and profile, and we still maintain our efficiency metrics that we're trying to go for. Like, we're not losing efficiency by coming over here, and we're very marginally affecting the total size the machine has to be. So that's where the falling film is getting implemented. Now, we're not done with flooded. Dunham Bush machines, the AVX series, they're still shipping with flooded evaporators. The metering device feeds into the bottom. They're fully flooded, the tubes, and then it comes back out the top. But they're controlling based off of liquid level anyway, without getting into crazy details. Like, these are still going into brand new machines. So let's just keep that in mind. But the benefits of moving to a falling film design is that lower total refrigerant required, and maintaining the efficiency of it. But we get into, I don't know, I'm sure there's things from an engineering perspective, like if we were mechanical engineers, there's probably a lot more reasons as to why one, not the other. And in terms of cost, R&D and development, proven systems, like this is a newer, now it's been around for a while, don't get me wrong, but this is a newer style of evaporator. I'm sure there's all kinds of patent disputes around this stuff anyway, because these have become the preferred by manufacturers. And so I'm sure in some cases, we still see these being shipped with flooded, just due to patent infringement issues to begin with. They don't want to get sued by somebody because of, they tried to copy what York did in the wrong way, and then York says, hey, that's mine, and you get into the whole tiffs there. Yeah, so RTAA, YVAA, RTHD, various ways. And then, you got your hybrid style. That the only people, I'm trying to think of somebody other than York that is using this, and I think that I can't think of one, because I bet you, because this is not a normal falling film design, that there's probably some patents around this, that York has a chokehold on this particular style. But the YK, their YMC squared, their YZ line, all of those use the hybrid falling film on newer machines, not your older ones. So you'll still have plenty of these flooded out in the field. So if that line is coming into the bottom of the evaporator, it is a flooded design, and you'll notice that the sight glasses are up higher on those machines than if you've come across one that has more of a flooded or a falling film design. They'll be a little bit lower down on the actual outer shell to be able to look in there. That is further just shows how we are, how we're changing the liquid level that's actually being held in that machine. So I don't know if that's something you may notice out in the field, is a difference that you'll see between the two, is kind of even where they're placing the sight glasses to begin with. Trying to think, is there anything else we need to add on this? Because let's just kind of recap the original question. You know, what types of chillers are likely to have falling film versus standard? Well, by standard, we mean flooded. That is the standard in the industry. And high-level answer, going to be your newer machines. And water-cooled, air-cooled doesn't have a major impact on that. Your YVAA is an air-cooled machine, okay? We do have plenty of flooded machines, of YV or AVX by Dunham Bush. That's an air-cooled machine using a flooded evaporator. So, and we see this with screw and centrifugal models. Now, your scroll models are usually either a DX evaporator or a brazed plate or a plated evaporator. So completely different design. They're like a DX, the refrigerant and water are switched. The refrigerant's in the tubes, the water is on the shell side, versus what we've been discussing here. It's the other way around. Our refrigerant's on the shell side, water's in the tubes. So, yes, that is what I have seen the industry do, and I do expect that trend to continue into the falling film side of things. I think as time goes by, overall, I do think it is a very competitive, and getting that refrigerant cost down is a major selling point for a system like that. Absolutely. All right. Let me kind of read through some of the comments. Yes, just seen it. Duplex screws. Okay, yeah. All right. So, whether it be duplex screwed or centrifugal, I knew I took a centrifugal approach to that. But duplex screw would be the same basic concept. And we've had those designs around for a long time. You know, was it the the Carrier GX? Yeah, it should have been the GX series and the HX series. Those would be examples of air-cooled and water-cooled duplex screw. You know, they were separate circuits as well, but the same basic thing. You know, we flowed from one side of the evaporator into the other. Yeah, all the same basic concepts. You still had the same lead lag control. Like all the same principles apply, despite whether it's screw or centrifugal. None of that really changes the basic operating mode that the chillers are going to try to stay in. At least as a kind of a default with current standards. Still looking into it, manufacturer literature. You know, Train has some pretty good reading on that with their CDH manuals. So I would suggest that would be a good one to read up on. Again, the principles of what Train is doing with the centrifugal side, and like it directly applies to what you're going to see, whether it be a Carrier, Train, York screws that are also duplex style. All the same core fundamentals, like with a lot of things in this industry, the core fundamentals translate without any issue. All that stays pretty well the same. So it's just learning those fundamentals to begin with. Mr. Stand for Justice, hello, how you doing? I've got an air-cooled reciprocating triller. In the reciprocating compressor sight glass, there are always bubbles in the oil. Is it bad? If so, how do we correct the issue? And I'm going to assume, you didn't notate. Some of the only recips that still are alive, there are some Copelands, but we didn't use Copelands too much. I think York was one of the few that did. So you're probably talking about a Carrier, which would be an 06E, 06D, Carlisle screws, or reciprocating specifically. That would be my expectation. You can correct me on that if need be, because that will kind of help. Again, the basic principles aren't going to change much, but the me being more targeted with my response will matter based off of the compressor. Still getting things dialed in with this new system and spending most of my week doing that flood recovery. I didn't get to make as much progress as I wanted, so just be patient with me. Okay. So, let's see. From Asia, the compressor is from Poland. Okay. Well, let's just get into it from a basics perspective. All right. So just for review, I have got an air-cooled reciprocating chiller in the reciprocating compressor sight glass. There are always bubbles in the oil. Is that bad? If so, then how to correct the issue? So let's come over here to our handy-dandy whiteboard. So in this case, despite the type of compressor, the core fundamentals of this are going to be pretty well the same. So somewhere on the compressor casing, there's going to be a sight glass, and we're going to be able to see some level of oil collected there. Now, in that oil, there's going to be some bubbles. Now, you could have a machine that's running perfectly fine without issue, and you still could have some light bubbles kind of forming around the top, and it's just creating this thin little layer right up here. All right. So those bubbles are mostly normal, and majority of these bubbles to begin with is going to be refrigerant flashing out of the oil. So as the oil and stuff circulates through the system, with a reciprocating style, we're not using oil separators or stuff for a chiller side of systems. Now, they do have some of that on the, I think the reefer side, the low temp side. But what we're doing, most of our machines are not going to have oil separation. So our oil flows through the suction line, has a very, basically just like a scroll compressor, or some of our lower end screw machines like a YCIV, everything gets blended. YCIV was a bad example because we do have an oil separator there, but a scroll machine is a better one where these get blended, the oil flows through the evaporator in the whole process. We try to minimize how much oil gets into the discharge line and carried out of the compressor, but on some scale, like we're not going to be able to eliminate all oil. It's going to be circulated through the system. So that being said, when that oil comes back to the evaporator, it's going to be bonded with a certain volume of refrigerant into the oil. Now, this is going to be vapor refrigerant being our suction line. So when this comes back in suction, hopefully you've got vapor refrigerant coming in, and that vapor refrigerant, while that oil is getting stirred and churned and all this stuff is happening in the compression process of just running the compressor, and it's basically a car motor, that refrigerant's going to flash or off gas out of that oil, and it'll just get taken up into the suction input ports coming into the heads to get compressed. Okay, very normal, not an issue. So having just a slight little call it foamy or frothy film right on top of that oil level isn't going to cause you any problems. Now, when it does become a concern is when you've got a significant amount of oil stacking up here, okay? So, or not oil, foam, okay? Or bubbles, however you want to rephrase it. So we start having major foaming action happening well above that oil line further up into the sight glass. And in some cases, you will see this completely fill the sight glass. So it's foaming far up above that. This would be evidence of you're having a low suction superheat. So your metering device is overfeeding back into the sight glass. And this would be one example, okay? So we'll start with the low suction superheat first, okay? So low suction we'll just do SH, superheat. Get our acronyms going. Okay. So low suction superheat would be one of them. Now, if your machine's not monitoring suction superheat, some of these would also monitor discharge, and you can run off discharge superheat as well. So a low discharge superheat is likely going to mean a low suction superheat. So we're just going to keep it simple to there. We are having a lot of either dents, or in some cases, if we're foaming up to the top of this sight glass and above, we likely have liquid refrigerant coming back into this compressor. And so what is happening is that heavy volume of refrigerant, specifically liquid, so that liquid will come. We'll just draw a little small compressor here for a second. Got our compressor head. Be a wonderful artist if you couldn't tell. All right, so here's our sight glass. Here's our motor, our crank, yada yada. So as that liquid refrigerant comes in, I should probably do a different color. We are going to see it come into the bottom of the suction line. It's going to go through the stator and motor, because that's part of how these compressors are cooled. And then if it was a gas, then it would get just drawn up as a vapor up into our head. But that's not what's going to happen with this liquid refrigerant. So this liquid is going to flow through down here, and then most of these compressors will have like oil drain ports, because there is a divider wall right here to support this bearing. So you'll have a bearing support here, here, and then some of them may have one back here, even though typically it's just these two. So these will be your two primary bearings for the shaft and for the rotor. So right in here, there will be like a drip leg port that's intended for oil. So as the oil comes in, it hits the stator, and the rotor gets collected and drains down into the bottom of this motor housing, and then it's able to drain over into the rest of the compressor belly, or the sump, the oil reservoir, however you want to phrase it. Well, when liquid refrigerant starts to come in there, it now starts taking the path of that oil. And liquid refrigerant is heavier than oil. It has a heavier specific gravity. And so it will start to collect down here. But our oil pump is also down here. So there's a lot of, or is pulling from the bottom. So there's a lot of turbulence. There's a lot happening. Most of these cranks will also dip into the oil and splash the oil around, in addition to just having the pump run. So there's a lot of turbulence in here. And that turbulence is forcing this liquid refrigerant to flash gas off and turn into a vapor from that liquid. Well, when that happens, we foam up, and all this foaming action is a result of that liquid refrigerant getting in here. And it actually doesn't take that much. It doesn't take a whole lot. You could have a fairly minor flooding action, okay? So where we're not just hardcore just flooding this compressor out, but it's just a very small amount coming in, but it's still coming in to begin with. It's not a fully saturated vapor refrigerant coming back into our compressor. When that happens, we will foam. So this is evidence of that. So again, depending on how severe your foaming is, will depend on whether you should be worried or not. And so now this is all in the context of we're already in operation. The compressor is already running. Now let's take this one step further. There's another common situation we'll run into, and that is at startup. So if our crankcase heater is not working, we have low ambient temperatures, something to that effect, another condition would be a flooded start. So with a flooded start, basically we're not necessarily have low suction superheat, so we can just kind of move on from this. But if we're inside of our crank here, crank housing, then as the machine is off, we need the crankcase heater to keep this oil warm. And by keeping the oil temperature up, we are allowing whatever liquid refrigerant does collect in the bottom of this of the compressor housing to boil off and flash back off and stay out of the oil. We want all that refrigerant out of there. Now, in the case that is not working, or there is some condition happening that's allowing that refrigerant to stack in here in a significant way, then when that compressor goes to start up, it's not going to sound good, first of all, because this whole process is actually, if that oil pump is pulling in oil into the pump and trying to move that through our crankshaft to lubricate all of our bearings and joints, that's not going to go so well for us, because that's how you put a lot of severe wear, beyond just risking breaking a set of valves and the piston and the heads themselves. You're putting a significant amount of stress because we're not able to. This refrigerant is not lubricating anything, but it is what's at the bottom of your sump. So that's issue number one. Issue number two, you're going to have a major foaming right out the gate. So as soon as that compressor turns on, it's not abnormal to have a little bit happen. That's not abnormal. What is abnormal is the first several minutes, or your sight glass immediately turns to straight heavy foaming as soon as that compressor cranks up. That is not okay. That is not normal. And in that situation, again, it comes back to the liquid refrigerant stacking in the bottom of the sump, or the oil reservoir, which is built into the compressor, and that getting stirred up is flashing that off, creating the foaming action. So those are the two main things that I would be worried about with foam if I'm having excessive foaming. If we've got whether we're at part load, full load, whatever, if we've just got a very minor amount, like I said in the very beginning, with this little blue line where it's just a little bit of action, I would consider that perfectly fine. I would consider that perfectly normal. I wouldn't be worried about that. It's when this escalates to the whole sight glass, or a large portion, it doesn't have to be the incomplete sight glass. If we get to where we've got a full standing column of foam happening like this, that's when I want to investigate. I just want a teeny little layer, if I'm going to have any at all. I don't want an actual standing layer of foam or bubbles happening in my oil sight glass. That is my red flag. And these are the two things I'm going to start investigating first, depending on when it happens. So if we're in operation and it's still happening, then I'm worried about my suction superheat. If we are only seeing it at startup, but then it starts to clear up, or even if it does maintain, okay, then a flooded start, which takes me to my crankcase, would be my next concern. And it is possible that these two coincide. If we are having a low suction superheat and we are starting to flood that compressor back, then but we also do not have a working crankcase heater, or it's been off for a very short period of time. So say the compressor is staging fairly, I don't want to say it's not short cycling, but it's staging fairly quickly is my point. Then these two could kind of coincide, where you're going to see flooded start conditions even if you have a good crankcase heater, because you're having a flooding issue with low suction superheat to begin with, and we've just got to get that liquid refrigerant out of there. So yeah, I do see. Okay, another question. I noticed that the chiller has a receiver on top. I'm genuinely asking, what is the two sight glasses on the receiver intended for? So let me pull this. One second here. Okay. I noticed that the chiller has a receiver that has two sight glasses, one on top of the other. Generally asking, what is the two sight glasses on the receiver intended for? Just monitoring your liquid level on a operational scale. So part of the liquid receiver's function is to help, it helps us get more liquid refrigerant into the chiller, or just holding a higher capacity of refrigerant to be able to handle major load swings. So when we're using a receiver, we may have certain conditions where we don't have a whole lot of load and we're not processing as much refrigerant through that system at that point, and we're going to have that refrigerant start to stack up more, versus when we have a significant load and we're going to have to flow a lot more BTUs through the system. We can do that by using a receiver. And I would say that I see this the most with single speed non-variable compressors, or they don't have variable capacity, even if it's something as simple as an unloader. So when we don't have that, then I will usually see a receiver implemented to compensate for that, to give us more loading and unloading capability based off of the load. And so then our metering valves are kind of becoming that control point, if you will. As the load reduces, the metering valves and how many compressors we turn off and on would be included in that, are matching load conditions. But then when we have a major load increase, so this would be what I'd expect from a process cooling or process chiller, so a little small application, breweries, CNC machines, stuff like that. We go from very minimal load during a standby state to then very significant load when the machinery starts up and begins to do its process cooling. Or this could be implemented in some custom application somewhere where you've got just a machine built to serve a set of machinery. So these are the applications I would expect to see this. In those circumstances, yeah, you're going to have major swings between your off-cycle loads and just trying to keep the chiller at a minimum state while the machinery gets ready to do its next run. And then once the next run starts, huge load influx comes in and adds a lot of it requires that additional refrigerant that stacks in the receiver to then be deployed to properly process down that load. And this is where, low temp walk-in freezers and coolers use this same type of tech. When they get an order in from, say, their delivery service, they need to be able to process that down fairly quickly. So that fresh order coming in, it may raise the box temps quite heavily, and we need to get that down to storage temperatures for whatever that facility needs, or the restaurant, whatever the heck it is. Now, we're talking chillers here, but just to bridge some parallels between what you'll see in that side of the industry versus this. They're dealing with a very similar thing, and why they need a liquid line receiver to begin with is so that when those major load swings happen, they get a truck delivery, there's enough refrigerant to support that coil and keep the system online without starving it, but then it has the capacity to choke itself off and back off once we get down to load and we're just kind of running an idle state. That's just another way of looking at having a process system and kind of their purpose and function. So in terms of the sight glasses, let's hone in on the sight glasses here. Those are just going to be a way of helping you determine how much refrigerant is in there visually. So visually being able to see your liquid refrigerant level. And I will say, be careful that we're not confusing a receiver with an oil separator. They can look damn near identical. Okay. So, just in case, if, 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 if your liquid line receivers are going to be after the condensers on your literal liquid line. So we're going to feed through the condensers, and it's going to stack into the receiver, and then it's going to flow out the receiver to your metering device, your load and evaporators, whatever the case may be. A oil separator is going to be between the compressor discharge and the condenser coils. So they will look very similar, and they'll use sight glasses like that as well. And it's very common on a oil separator to have those sight glasses so that we can monitor that our oil levels are within specification. And we can do that just very quickly, very easily, because those will stay fairly consistent. Oil levels won't have major spikes and dips in that whole bit like we would do with a process system in the liquid line receiver. We're going to see that receiver level have fluctuations depending on our load conditions. We're not going to see that on the oil side. So those are the two locations that those would have. And the oil separator is going to have the discharge line in. You typically on the side, have a outlet port leaving out the top of it, and on the very bottom will be the oil return line going back to the compressor. So just be careful when everybody's out there that we don't confuse an oil separator from a liquid line receiver. And I would only expect to see systems implemented with liquid line receivers in those process environments where we are trying to have those heavy load swings, and especially if our compressors don't have variable capacity, because even if we have multiple compressors to turn off and on, it's not really the same thing. While it's one version of it, it's a rudimentary kind of first step. Having the compressor itself be able to ramp down and stage down is more effective, and that's why we don't see a lot of liquid line receivers implemented on a lot of, say, our coolings or comfort cooling styles of chillers and such. We don't see that implemented a whole lot. In my opinion, why that is because we're using variable capacity compressors, whether it be via slide valves, whether it be via unloading heads, if we're talking reciprocating, or whether it be, your, not that centrifugals would use receivers, but you've got your IGVs, your inlet guide vanes, or we've got variable speed, and we're able to speed the compressors up or down. That does a lot of the work, in my assessment, the way I see it and I understand it, that our liquid line receiver would be doing if it was in the system and we had some version of that implemented. Really good question, though. All right, we still got some time. If y'all have more questions, feel free to put them into the chat. I do still have some backlog questions that comes in through the channel that we can get to if need be. But I just hope everybody's having a good day, good start to your week. I hope things are going well for you. I hope that there's a lot of weather events and stuff going on right now, especially here in the U.S. I'm not as familiar about globally, but again, things are always happening. I hope everybody's staying safe through all of this. It's a weird time. It's a weird season. This kind of weather is, at least what we're having where I'm at and here in Texas, not normal for us by any means. Any other questions? If not, I'll probably move on to the next one on the backlog. Okay. Let's see. This is a fun one. Let's get it booted up here. Yeah. So in terms of the EXV being able to limit load, most EXVs can actually turn down completely. Uh, with an so I'll answer it this way before we get to this next question. With a TXV, TXVs work many times our limiting factor, as a TXV could only unload to about 30% of the rated capacity. And once we hit that 30% mark, so let's say we had a 10-ton valve for simplicity, because I'm not that great with math, or here we go, we'll make it sound larger. We have a 100-ton valve, okay, TXV, they do exist. So we have a 100-ton valve, and for most TXVs, we were only able to derate them down to about 30 tons. So that would be 30% of the total capacity. And in many times, our compressors and such can scale beyond that. Can. So that created more of a limiting factor. With an EXV, though, we have the ability to literally just barely even crack that valve. So what your question is specifically, what becomes the limiting factors? The limiting factors actually start to become the compressor's ability to derate or unload. How far can it get itself to a minimum state and still be okay to run? Centrifugals are going to struggle with this more than, say, a positive displacement, just because they're aerodynamic, and we don't have to dive into those details right now. But and then the other side of it is your evaporator superheat. Okay, so we have to maintain above freezing temperatures unless we're running a brine loop. But in a general basic sense, we can't get to below a freezing saturation on our evaporator. That's risky with water. Most of the time, we never want to process our saturations down below 35 degrees. We want to give ourselves a few degrees of buffer, especially given our tolerances for our sensors like transducers or thermistors. We usually have a few degrees or a couple of degrees of variance that we allow. So let's say you were using a transducer and it was reading a few psi off, and that few psi meant 2 degrees or 3 degrees less of saturation, which might be pushing the limits of what we'd normally allow, but was technically usable. Well, if we tried to run closer to that freezing saturation, well, then we push beyond that 32 degrees. So 35 is the recommended, given the tolerances we allow for our sensors in the industry. So yeah, your suction pressure, suction superheat, or suction saturation, those become major limits as to how far down you can go in terms of unloading. Your compressor's ability itself, and then to add to the compressor's ability, a lot of our compressors are they use pressure differential to flow oil. We have to maintain a minimum differential. If we unload the machine too far, then at some point we start losing that minimum DP, and that creates its own problems with oil flow for the compressor. Or we could run into issues where we're stacking oil in the evaporator because we don't have enough velocity to carry that oil back. So my overall point being, the EXV doesn't become the main limiting factor. And technically, most of the time, a TXV wasn't either. But we can do a lot more with an EXV that we could not do with a TXV. Yeah, hopefully that makes sense. That's a fairly high-level answer to that question. Still a great question. It's these are important things to distinguish and understand the whys behind it, and backing that why up as to what makes the different components different to begin with, and how we should expect them to react and change and do what they do. Okay, let's get into this question. Oop. Let me. Come on. There we go. Will you please guide me the proper procedure to drain, change the oil of CVH train chiller, how we will drain the oil since it has negative pressure in the oil sump. So to completely drain that oil, and we're not going to go through a recovery process, okay? We just want to drain the oil out of the machine to change it, service it, whatever the case may be. There's lots of circumstances where you would want to do this. Again, in the context of we're not recovering the charge, we have to pressurize the chiller. Sounds like a overly simplified answer, but it is the truth of it. So we have machines that we call them pressurizers, okay? So they're essentially these little carts that you can roll up to the chiller, wired into a power source, whether it be the chiller's power source somewhere or an external one, whatever the case may be. And basically they'll have their own little circulating pump, and they'll have typically an electric heater built into them. And so what this pressurizer is doing is it's flowing typically condenser water. Usually we'll hook this to the condenser side through its little heat exchanger that it has built into the little package cart that it is. And we'll get that condenser water temperature up. And many of them will have like a transducer that you can put on the chiller. So we want to get to say 5 psi. So it's going to continue heating that water up and heating that barrel up until the temperature gets up enough. Now, in this situation, we're going to be completely isolating all of our water valves. So condenser water, chill water valves, everything should be isolated. We don't want to have flow, because flow is going to this doesn't work if we have flow through our heat exchangers. So we want it completely isolated, and then by putting all that extra heat in there and heating the tube bundle up, we can get the refrigerant to increase in pressure and get it up to our set point. Now, if your machine doesn't use a sensor to monitor the chiller's pressure itself, then you want to just be very mindful to do that yourself manually. You don't want to over pressurize one of these, because then we blow a burst disc or rupture disc, and then like life's not so fun after that. But yeah, the pressurizer, it's just going to circulate water through a heater and its little pump that heats up the water, gets the pressure up. Once that pressure is up, then you can just hook up and you can drain the oil down. It's not a big deal, just like you would do with any positive or high pressure machine. It would work the same at that point. You just drain it out into a bucket, and depending on what your preference is, you can either allow the chiller, if you allow the chiller to cool back down, say you opened up you stopped running the pressurizer, you've already drained the oil, like you've got it up to pressure, oil's been drained, you're ready to add more oil back in, you've got two options. Remove the pressurizer connections, get flow back through the chiller, let it come back down in temperature, and then just allow the refrigerant's standing vacuum to draw that oil back in. Or you could use a pump and just pump the volume of oil you want back into the machine. I personally don't really have a preference either way. I think it kind of depends on what the circumstances are, what my reasons for changing the oil are, what equipment do I even have available to me at the time. So there's a lot of variables that goes into which one I would choose in the moment. But that would be the basic process. Pressurize the chiller. That requires that equipment. Okay, let me take a step back. If you don't have a pressurizer, I have successfully, on smaller machines specifically, I have successfully isolated the condenser water lines, isolated all that. We had a mop sink that was close enough. I hooked a water hose to the mop sink, ran that to the condenser, and then just turned it on full blast hot water. Now the facility has to have the capacity to keep up that hot water because this is going to take a long time. Um, this is not a fast process whatsoever. And you're going to burn through a tremendous amount of hot water. So they better have a good water heater, boiler, whatever the heck they're using. It better be sufficient. If they're using any kind of light commercial or just like standard water heater setup, this is probably not going to work. Anyway, so if the hot water is sufficient, then you can push that hot water through that, let it drain out the barrel. Now, this is going to screw up your chemical balance and all that, so just keep that in mind. It's not going to be a major screw up because you're not affecting the entire condenser water loop, but whatever section you are connected to, like you are dumping those the chemicals for that loop down to a drain. Either way, you're going to run a drain line out the bottom of the barrel to whatever drain you have, whether that be outside floor drain, whatever the case, and just flow the mop sink water through there. So if you absolutely just had to have a option and you don't have the ability to get a pressurizer at the time, that has worked for me in the past. But I would highly recommend investing in the pressurizer and being able to do it what I would consider the correct way. All right. Yeah. So that's going to be your main processes, okay? So we've got it up to pressure. We drain it down. We can add the oil back in. We're back online, and we are good to go. And that's going to be, this is a same concept for any chiller. This isn't just specific to Trane. So if we have a low pressure chiller, which we're having a lot more of these get into the market. Now, granted, the new ones, like the YZ coming into the market from York, that's in mag bearing, so there is no oil there. But whatever low pressure chiller you're looking at, this is how you can pressurize to remove that oil. Now, if we're talking about doing a recovery, and well, I mean, heck, at that point, we can just, once we're recovered the refrigerant, just pressurize the thing with nitrogen, and you can push the oil out that way. Not a big deal. But specifically in the context of we are trying not to do a full recovery. It's a really good question. Right. Okay, well, it'll take a couple of more minutes. Does anybody have any other questions? I'll take some more questions out of the chat. And then yeah, if anybody is not already a part of chilleracademy.com, I'd love to work with you over there. I've got a free service training course that you can get enrolled into. That also gets you into the newsletter I send out twice a week. So in that newsletter or email, basically, I'm just going through and kind of explaining some basic stuff. I'm taking very similar to this format where I'm answering genuine questions I receive. I'm taking questions that I get and I'm putting them into an email and giving a breakdown and explanation via an email and sending that out to you. So if you're interested or if you want to be a part of that, again, it's completely free to go in and do that. You can sign up, enjoy the whole process at chilleracademy.com. Really love to work with you there. I mean, it is our mission. It is my mission that we need new, better methods of training our technicians in this industry. And if we do not start to adapt to modern technology, we're only going to continue to struggle further. I think looking at it, we're on a global scale, we lack, I think it's 45% of what we need to actually support our industry. And majority of that is on a commercial scale. So that's an interesting thing. You know, a lot of like general public that are not part of us in the HVAC trade almost always think about residential as kind of like the first thing in their mind. Well, that's because that's what their brain is, and it's also one of the easiest ones to get into, yada yada yada. But in reality, when you look at the metrics, residential is a small piece of the total work and volume that happens in this industry. And it's like, I think it was between 20 to 30% uh, of the total work or cash flows of the industry is actually in the residential sector. The other 70 to 80% happens in the commercial side. That is us and what we're doing here. And we need to increase our teams by 45% to actually support industry needs right now. That's just right now. So I really like, this is my Chiller Academy, and what we're doing right here, right now, having these conversations. These are ways that I think we can overcome this, and we can get the knowledge, experience, and support we need on a global scale back into this industry so that we can really help a lot more technicians. This is a very critical mission. What we're doing is critical infrastructure, okay? A lot of our cities run off of district loops. They need those city loops to function, to make the whole city function properly. Our state capitals, all of our government facilities, those are chiller systems, so chill water. They need us to keep them online. All of our data centers, those are all going to be chill water systems, especially the larger ones, the major ones that are the most important. Chill water. We've got to be there to be able to keep that online. Like, our needs to support things in our society is way too much for us not to take what we're doing as HVAC technicians who do chiller work seriously. Anyway, my point is, that's my passion. That's what I'm doing here, and I really, really want to work with you. I see y'all in there, Sterling and Mr. Mike Frylock. Let's see how you doing. It's okay, Sterling. I get it. You're across the pond there, so you work on a little bit of a different time scale than we do. Granted, I choose to do these in the middle of the workday on a Monday, so that's also great. That's great for everybody's schedule. But it's what works for me at the moment, so I do what I can. Could you explain dew point in cooling towers and why you can't cool the water down below dew point? Thank you very much. Yeah, by dew point, I'm going to hone in on wet bulbs specifically. And just to make sure, Sterling, before I go on, and before I explain this, by dew point, are you meaning wet bulb? So wet bulb is specifically the metric we use. So is it, I just want to make sure I'm coming at this from the right way for you. If I go the wet bulb approach, is that going to mess you up? Yes, wet bulb. Okay, perfect. We've all got different backgrounds. It's important that we're on the same page, because if I start using the wrong terms or different terms than what you're needing me to use, then we get all kinds of sideways, and that just didn't help anybody. Okay, let's get into the question. So could you explain dew point in cooling towers and why you can't cool the water down below dew point? Thank you very much. Yes, so it's not dew point, it's wet bulb. So we're getting into just basic psychrometrics at that point. Wet bulb is the value that our towers are going to compare to. So this is what we call tower approach. All right. So tower approach is how we define how efficient a tower is. So the lower the approach value, the better it's exchanging heat to the ambient outside air, and the better it's functioning. So when we want to see how a system is operating, that's the values we're going to be looking at. Is, okay, what is our wet bulb temperature? What is our tower approach temperature? So wet bulb and dry bulb, real quickly, is your dry bulb getting into just real high level, real fast psychrometrics. We're not going to get deep into this because we don't need to. All right, so your dry bulb, dB, is your sensible temp. Sensible. I swear I had some spelling classes. All right, so it's your sensible temp. So basically, this is just ambient temp you read with a thermometer. It's ambient, okay? So this is what you read with a thermometer. All right, this is what you feel. Then we have wet bulb, which plays off of dry bulb. Okay, this is basically a measure of how much humidity we have without saying relative humidity. That's a B. Humidity, whatever the hell. Okay, so we have dry bulb, wet bulb. So with a cooling tower, we can cool down below dry bulb temperature because we're using evaporative cooling in the first place. So we have, if we have a 100-degree day, we can still make 85-degree condenser water. So the dry bulb aspect is not what's important to us. It is the wet bulb aspect. So on that 100-degree dry bulb day, we may have an 80-degree wet bulb. And if we have a tower approach of 5 degrees, then we can make 85 degrees. Okay? Real basic levels here. And that is the approach. Just to give, again, very quickly, I don't want to get deep into this because I don't feel like we need to, but I do want to just give some context because tower approach is a major factor to this. So our TP, tower approach, equals our wet bulb minus tower leaving water. Okay, so this is the water leaving your tower, whether it be a closed loop system with a heat exchanger or whether it be an open loop coming out of the basin. Either way, you subtract these two from each other and we get our tower approach value. Now, it's a 5 to 10 degree tower approach is very normal. Okay, so 5 to 10 Fahrenheit specifically is very, very normal tower approach values that we could see on a routine basis. That comes back to the cooling tower. Its design, manufacturer sets those parameters, not us. Okay, now the question is, why can't we cool the water down below that? Well, it comes down to our ability to evaporate. Okay, so as a cooling tower is raining water down over the fill media, we're allowing evaporation to happen. Evaporation allows a cooling effect. The same way our skin evaporates sweat, we do that to cool our skin down to help regulate body temperature. A cooling tower is effectively sweating by having that water in the tower basin flow over a fill media with a fan to create evaporation. And that evaporation cools the water that stays liquid down, because the water that turns into a vapor draws heat from what stays liquid. Hopefully that, yeah. So it's just drawing the heat, and we're sending that vapor out with its heat, and the liquid left behind is now colder than it was. Now, the limitation we have is wet bulb is indicating to us how much humidity we have in the air, which means that we can only evaporate so far. Our liquid temperature we can make with evaporation can only go as far as our wet bulb temperature is. And the wet bulb temperature will always be less than your dry bulb. It's not possible that they would reverse. Okay, to give an example here, if you're swimming in the lake and your entire body is submerged, at that point you are 100% wet bulb to your dry bulb. Okay, so a 70-degree dry bulb at that point down in that water is a 70-degree wet bulb. Not a whole lot of evaporation going to happen down below the water surface. Just to paint a picture as to the relationship here. So, we want to get as close to that wet bulb temperature as we can, which comes back to our tower approach value, but we are limited by that temperature. And it comes back to how much we can evaporate given how much humidity is already in the air. So if there is very little humidity in the air, then we can evaporate a lot more water easier, which means that we can cool our liquid water that stays far lower. We can get much lower temperatures because we have a lower wet bulb. So that is the basic relationship between the wet bulb and our leaving water in terms of what a tower can do. It comes back to evaporation or the tower's ability to sweat that water off. Does that actually answer the question you're seeking? Because I want to make sure that actually resolves the question there for you, Sterling. Let's see, I see you in Frylocker. Web bulb. Yeah, I mean, the psychrometrics it's one of those things that makes it's hard. It is. Like, there's a lot of basics to it. We get better at it. Some people, there are some who try to say it's super easy, and it depends on the person, okay? I could get off on a rant if I really wanted to, but yeah, like Frylock said, it's tough. You get into a lot of science with it. Sweating is part of psychrometrics too. That's why I can. That's funny. That's a good one. That is a good one. Yeah. Yeah, we are cooling towers. Yeah, exactly. That is a good point. Like, we are a example of how a cooling tower functions. I really like that. If you check your weather app, yeah, it feels like, yes, it feels like temperature. Yeah. See, these are good points. Good job, Mike. Yeah, somehow, whenever I try to wrap my head around it, I go off on high head. The analogies are awesome. I kind of struggle with the whole wet bulb concept as in exactly what it means. Sterling, are you familiar with a sling psychrometer? This is how we discovered how to measure wet bulb in the first place. So if you're familiar with it, then I won't completely rehash what it is. But if you're not, I do want to explain it, and that it might help. So a sling psychrometer, not a digital one, but a sling. Ready to come join? You never know, Mike. Might get the call soon. There's a lot going on right now. I've heard about it, but never used it. Okay. Well, then let's cover a sling psychrometer from a very quick high level here. Okay. So let's actually represent this on the whiteboard here. So we all are probably familiar with a regular psychrometer, okay, digital. With a sling, we had a little handle. Okay, this is my handle, and then we had this little apparatus that would spin on this handle, and you'd literally swing it and spin it around. And what this thing had in it was two thermometers. Now these were typically mercury bulb thermometers. Okay, so we had two thermometers that would stick out of it. One of them would be left with nothing on it. The other one would have this little sock, little cotton sock put over the top of it, and that sock would be wet. Okay, so you'd get this sock wet on top of that thermometer, and you spin this thing around. And as it spins, evaporation starts to happen on that sock. Now it takes a few minutes. You have to just keep going, keep going. And after a few minutes of spinning it, you'll see that this second thermometer is colder than the first one. The first one is going to be at ambient temperature. This other one is going to be our wet bulb temperature. This is how we started to measure wet bulb originally, and the development of psychrometrics began as a theory. So this wet sock will change how much it cools based off of how much moisture is in the air. The more moisture that is in the air, the higher our relative humidity. The less evaporation happened, the less the thermometer cooled down. So it was much closer to the dry bulb temperature. But if we had if we had ambient conditions where we had really dry air, there was very little water in it, then a lot of evaporation happened on the sock, and the temperature cooled down significantly, and it was much lower than the dry bulb temp. And we'll actually, so this one was your dry bulb, this one was your wet bulb. So this is how we began to measure this, and then the rest of the psychrometrics chart and the theory and everything around it began to get built off of there, and what we have today as the modern psychrometrics chart that we use for engineering. So the wet bulb temperature is completely dependent upon how much humidity exists in the air already, which we commonly say our relative humidity in just kind of general speak on a daily basis. So when we say our relative humidity, we get that because we know what these two numbers are, is my point. So a low relative humidity means lots of evaporation. A high relative humidity means less evaporation. And the more we can evaporate, the more we can cool something down. The less we can evaporate, the less we can cool. So this is where a tower, because the tower is an evaporative cooler, it is limited to what this wet bulb condition is. And this is also true for, like, say, swamp coolers and stuff, which honestly, Sterling, I know you're not in an arid environment, so I know that you may, I don't know how much exposure you have to something like that, but swamp coolers all serve or have the same issues and the same basic principles, where they can only cool as much as there is humidity in the air to allow them to evaporate. So from this, say, addition or perspective, does the sling psychrometer piece of that kind of help tie that together better? And just kind of understanding where we can get that, because you can make a sling psychrometer yourself, right? You don't have to buy one. It's very easy to make, and you don't have to use a mercury thermometer or anything like that. Like, you don't have to use one of those. You can use a digital thermometer and just put a piece of wet fabric on the tip of it where the sensor is, and there you go. You've got your wet bulb reading. by just kind of slinging that around. And actually, early on, before I had a digital psychrometer, the little K-type thermocouples we would get with our meters. Of course, I was using field piece at the time. That's what we would do with them. I would put a little piece of like rag on the tip of it, get it wet, and I could sling it around in my hand and just get it moving in the air and get a wet bulb temperature, and then take it off and get an ambient temp. And there you go. You know exactly where you're at on your psychrometric chart. So hey, struggle exactly what it means. It means how much. It's another way of saying relative humidity. Maybe that's an easier way to bridge that gap. It's just a different way of saying it, and we use a different number, but it means the same thing. It means the same thing. Call it a more scientific way to say it, or a more technical way. How you doing, Jason? I see you in the chats, bud. Good to see you, man. It's fun. I saw your post about was it a WMT coming into Central Texas here? That's going to be super fun to have one of those. I'm really excited about what Daikin does with that WMT series. With recovery is going. Cover up your temp probe with a wet. Yeah. So here we go. Whip around like a cowboy. There you go. Yeah, Michael's already on that. No low point. So conventional recovery was, yeah, that sucks, Jason. I hate how they do that, man. I just make it easier for us. I don't know why they can't just give us a recovery port that makes sense. Especially at the scale we're operating at. It wouldn't take nothing for them to add that. I rather enjoy conventional recovery these days. Under a 10, you can tell. Should I also dress like a cowboy? Yes, and send pictures. Not only dress like it, send pictures when you do it. Trying to catch up on the 250 pounds. The closest zero get. The closest you get to swamp cooler is when recovery in gas phase with wet towel. Yeah, okay. Yeah, that's what I expected. So I knew that reference probably would mean a lot less to you, which is fine. Okay, so if wet bulb is relative humidity, it makes more sense. Okay, perfect. All right, so yes. All right. Then we made progress, okay? Even if you don't leave today fully understanding it, that's fine. We made progress, and that's what we got to stick with. It's a painful concept to get your head around, okay? All of us go through it, man. All right. I saw Mike had a question up here earlier. Cooling towers work. Maybe okay, now what you were answering originally. Okay, I see it now. I love push-pull. Yeah, push-pull is awesome. You know, in my opinion, especially, again, if you're going back to speed and efficiency of the transfer, I guess crazy what you can do with push-pull. And it's insane to me that it's just not taught very much at all. Like, it's just not, until you just get into the heavy side like what we do, it's just not a thing, which I guess fine, fair enough. It's smaller systems, it's such a small volume of refrigerant. Maybe it's a far useful metric. Fair enough. All right. I think we're gonna wrap it up, guys. Great chat today. Really enjoyed this. Reminder: next week there will be no live. I will be in College Station for fire school. So I'll be there for a full week. We will not be doing a stream, but we will pick up immediately following that next week when I get back, and we'll continue with this conversation there. If you are not inside of Chiller Academy, really love to work with y'all over there. It is this is my life's work. All right, this means a lot to me, and this means a lot to the industry that we as a whole are successful with this. And I'd really like to be a part of that in your journey and in your process, and helping you through this. Like this is not an like this is the elite side of our industry. I want to keep emphasizing this. We are in the elite side of it. We're not the only elite side of our industry, but we are in the elite. Okay, this requires a whole nother level of understanding how this industry works to do what we do. And the fact that y'all are here in the first place, good for you and good job. Keep it up. Don't stop. It is hard. It's hard, and that's why so few people are getting into it. But if you can keep going, you're only going to continue to get better, and you're going to continue to conquer and just have the life you want to have. All right, that's what it comes down to. You get to have the life you really want to have by sticking through this difficult journey. So if I can help you achieve that better through Chiller Academy, I'd love to do that. And if there's something that Chiller Academy can do, if there's something I can build inside of there that would serve that purpose for you better, let me know. Let's talk about it and let's brainstorm on it, because I don't have all the perfect solutions, but I'm trying to provide the ones that I do know I can do and I can think of on my own. Yeah. Anyway. Absolutely. Hey, thanks for coming in. Is it Stand for Justice? We'll just call you Justice in here for short, you know. Thanks for coming by. Good to have you. Good to see you in here. What are you doing in fire school? I'm a firefighter now. So there's that. So I've been, so Mike, I spent all of last week in Ingram. I was part of the recovery efforts up there. So anyway, this year I'm taking an ag recovery class. So basically, if somebody has a tractor tire fall on top of them, or they fall into a grain silo and sink to the bottom, I get to go learn how to try to recover them and not die myself. That's the high level gist from what I understand, at least. So yeah, it's good to see you, Sterling. It's really fun having you in the chat, bud. I'm right at the bottom of the barrel of the. Hey, we're all there at some point.